Welcome back to the Illumination Talks. This is part 2 of my talk on the mechanisms that control ice ages. And it's taken from my peer review science paper, which is entitled The Modulation of Ice Ages via Precession and Dust Albedo Feedbacks. And this has been quite an influential paper, I suppose, because it's been downloaded some 20,000 times, which is quite high for any peer review science paper. But I don't imagine you've seen it in the media very often, because it is somewhat heretical. We left part 1 with ice ages being controlled by albedo and dust, reflectivity of the ice sheets, and then dust getting on the ice sheets to reduce their reflectivity. And here is an image of this sort of reflectivity decrease you can get. This is dust on a modern ice sheet, and you can see how dark they can become if you get, this is industrial dust from, mostly from China, getting onto the ice sheets. And this is not 1 year's worth of dust. This is dust concentration on the surface, because the ice can melt and ablate and leave the dust on the surface for the next year. And that's why we get ice of this color. And that makes a big difference to the absorption of insolation or sunlight during the next summer. So how do we know that dust in the ice ages is causing warming and not simply consequential? The first clue, I suppose, is that during the ice ages, dust precedes each temperature rise. So in this graph here, we can see temperature on the top in red and dust on the bottom in green. And we can see here that the green plot precedes the red rises. So we get a rise in green dust, and then that is followed by a rise in the red temperature. So dust is preceding temperature, and so it looks like that dust could be controlling temperature. Another way of showing that dust is causal to temperature rises is to prove that the dust is intimately linked to the ice age cycle. So what causes dust? Why, after, say, 80,000 years or 100,000 years during the ice age cycle, do we suddenly get a lot of dust? And very, very high peaks of dust at that. So where did this dust come from? And what type of dust is it? I mean, is it volcanic? Where did it come from? Well, the isotopic analysis of dust in the Greenland ice sheet that still remains shows that it came from the Gobi Desert. Well, currently, most of the Gobi is not a desert. Most of it is actually steppe grassland. But we know that it was a desert during the ice ages because of the deposits on the lowest plateau in central northern China, where there are layers and layers and layers, tens of meters, hundreds of meters thick, of the dust that's come off the Gobi Plateau. And it's built up a load of strata over that region from the last million or more years, showing that the dust increases during the ice age maximum when it is coldest. But why does the Gobi produce dust during the ice age maximum? Why does it become a desert at that point? Well, scientists will say that these new deserts formed across the Gobi are caused by cooling and aridity, a lack of precipitation. But sometimes I think that these scientists have a bit of a one-track mind. They can't see anything out of their global warming box, because the PMIP3 maps demonstrate very little change during the ice age maximum. PMIP is the Paleoclimatic Modelling Intercomparison Project, PMIP. And they've produced various maps for the during the ice ages, and this is the map of temperature during the ice age maximum, which was about 20,000-30,000 years ago. And as you can see, it was much, much cooler in the north, in North America and in Siberia. It was much, much cooler, up to 20 degrees cooler at its maximum. But the rest of the world, across the tropics and the temperate regions, that sort of light green across the center of this map was not actually that much colder. That light green is only 2 degrees centigrade cooler than modern temperatures. And clearly that's not enough of a temperature change to make a desert out of the Gobi. So what about precipitation? Well, this is the PMIP precipitation map, and the white areas are no change in precipitation. And you can see the white areas cover most of North Africa up into Asia, and the yellow areas there are very little change in precipitation all across the sort of Gobi region. And indeed, the Chinese scientists have done a lot of research on rainwater basins within the Gobi, and they have demonstrated that in many places there was more precipitation during the Ice Age maximum than there is now. So it seems clear from this that the desertification of the Gobi region was not caused by cooling or a lack of precipitation. So the impression we're given is incorrect. But if scientists are wrong, then what else can cause a desert? Why does the Gobi region go from a steppe grassland, where there is ample grazing today, into a fully fledged shifting sand desert? So what else will cause a desert? Well, apart from cooling or precipitation. Well, the other things that might kill off plant life are nutrients, lack of nitrogen, lack of sunlight for some reason, or a lack of CO2. And we'll go through the reasons why CO2 will affect plant life in a minute. So which of these will change during an ice age? Well, we've already seen one. We've seen that temperatures will change. And on this graph, you can see that CO2 changes as well. So this is a plot of temperature versus CO2. So temperature is in red and CO2 is in the blue. And you can see they are in step with each other. They correlate very nicely. So both temperature and CO2 change during the Ice Age. They both fall during the Ice Age maximum, when it is coldest. So which is responsible? Well, the temperature changes. We've seen that the temperature didn't change very much within the Gobi region because these temperature changes are regional. The very strong temperature change showed here is for the northern hemisphere up in the Arctic Circle, where the temperatures do change a great deal. Meanwhile, the blue plot is of CO2, and CO2 is measured globally. It's a global gas, and so you can only measure it globally. And so the CO2 will have an equal effect in the Arctic as it does in the temperate and tropical regions. So it's more likely that it is CO2 causing desertification and not temperature. So is it doing so? Well, the only way to find out is to plot them. So let's plot CO2 versus dust, and here we get the graph, and you can see that CO2 and dust are highly correlated. So this graph needs a little bit of explanation because the CO2 is in blue, and you can hardly see it because it's covered up with the green, and the green is dust. But the dust plot has been inverted, and I've inverted the green plot so it corresponds more with the blue plot, so you can see how they rise and fall together. but it's inverted. So just in explanation, you can see 1, 2, 3, 4 or 5 peaks to the left. You can see the top of the blue plot. Blue is CO2. And as it falls, it goes down quite considerably. The green plot is actually increasing because it's inverted. So as CO2 reduces, dust increases, and they are highly correlated. So dust is inversely proportional to CO2. And also, it's not obvious on this particular graph, but the dust plot is logarithmic. So there is a great deal more dust increase to the amount of CO2 decrease. But we've put it onto a logarithmic plot so that they match each other. Otherwise, the green plot would disappear way off the bottom of the graph somewhere, because there is a lot more dust generated by a very small CO2 change. So, dust and CO2 are highly correlated. But is the CO2 causal of a dust increase, or simply consequential? Well, the way to find out is to find a mechanism. Why is CO2 causing dust increases? And the answer is that CO2 is essential for plant life. CO2 is a plant food. It's one of the most important gases in our atmosphere. Without CO2, all plants die. And at the pre-industrial concentrations of CO2, which is about 240 parts per million, plant life can thrive. But when we get to less than 150 parts per million CO2 in the atmosphere, most plants will die. So 90% of plants will die, and therefore 90% of animals will die, because plants lie at the bottom of the food chain, and if you lose the bottom of the food chain, everything above it will also die. And this is shown very well in this image, where we have 4 plants grown in different CO2 concentrations. So to the right, we have a plant grown in 700 parts per million. That's nearly double the CO2 concentration we have now. And you can see it's a healthy, strong plant. To the left of that, it's 350 parts per million. That's almost like today's concentration of CO2. And you can see a slightly smaller plant. Certainly its root system is smaller. To the left of that is 270 parts per million. That's almost like the pre-industrial CO2 level. And again, the plant is much smaller. And to the left of that, we have 150 parts per million, which is the sort of like glacial maximum concentration of CO2. And we can see a very small stunted plant that's not growing well at all. And you might say, well, this plant is growing. Yes, but it's been proven that stunted plants like this, grown in low CO2 conditions, cannot complete their life cycle. They can't reproduce. And so within 1 generation, this plant will be exterminated in a region with low CO2. So CO2 is essential for life. Without CO2, plants die. And as we've seen during the Ice Age, CO2 reduces, and it reduces to a point at which plants can die. And therefore we can end up with CO2 deserts, which is a lovely descriptive term which tells you exactly how these deserts form. And scientists will love to talk about precipitation deserts, dry deserts, but they won't mention CO2 deserts, even though we know they are a possibility, because it goes against their global warming belief system. They don't want to mention something other, something negative about CO2. And remember, the Gobi Desert lies at high altitude. So the plants there will be running out of CO2 much quicker than at sea level, because there is less air pressure at high altitude. It's like you climbing Mount Everest and running out of oxygen. You do so because there is less oxygen up there. The air pressure is lower. And the plants on the Gobi Plateau will do exactly the same. They will be affected first before any plants at low level. And so the Gobi Plateau will become a CO2 desert. Its soils will be denuded and they can be eroded by winds and then blown across the lowest plateau, as we know they were, and blown across the Laurentide and Greenland ice sheets, as we know it was. And just to show you how much dust there was, this is an image from Greenland, which shows Ice Age dust in situ there, actually now, today. So just to show you what this image is showing, to the right we've got ice that was deposited, say, 25,000 years ago, quite a long time ago. And as we progress to the left, as you look at it, so that ice gets younger and younger and younger. And then we hit the double band on the left there, which is the Younger Dryas, and that was about 13,000 years ago. So you can see how much dust was deposited on this ice. And remember, this is way up in Greenland. This is much further away than the Laurentide ice sheet. They estimate that on the Laurentide, there was something like 10 times or 20 times as much dust deposited as here up in the high Greenland ice sheet. So the Laurentide ice sheet would have been much darker than this. And remember also that this dust gets concentrated as the interglacial proceeds, as the ice starts to melt. Because, as we've said before, the ice melts, it can melt, it can ablate, but obviously the dust can't, and it remains on the surface. And so the dust we see here on this ice sheet in Greenland can be concentrated until it looks something like this. And it can go even worse than that, because this is me up on the Baltoro Glacier up in the high Himalaya, and I'm standing on a glacier, on an ice glacier. And it might not look like a glacier, but most glaciers don't look like an icy glacier as you traditionally think they will look, because the ice on the surface gets ablated, it gets melted, and all you're left with is the stones that have fallen on top of the glacier. And so I'm standing on 100 meters of ice, but all you can see is the top layer of stones and dust that are still concentrated on the surface. And it's that dust that lowers the albedo that causes the melting. So now we have a complete mechanism for the Ice Age cycle, which has never been explained before. Nobody knows how the Ice Age cycle works, which is, in the 21st century, that's quite amazing that scientists still don't know how the Ice Age cycle is modulated and operates. But now we do. But only because you tune into the illumination lectures. So this is how the Ice Age cycle works. Here is a graph of an Ice Age cycle, and you can see from the peak in the red is the temperature plot. The peak in the red is an interglacial. It's very warm. It's like it is now. We are in an interglacial now. But then the blue plot, which is the insolation plot, that's the orbital cycles changing the temperature in the northern hemisphere, changing the amount of insolation, the amount of sunlight in the northern hemisphere. The blue plot plunges, and you can see that here, that the blue plot goes down quite low. And that's quite a difference. It's like 20% change in the amount of sunlight, hitting the high latitudes of the northern hemisphere. And the temperature cools, not surprisingly. And so the red plot plunges in line with the blue plot, and we get cooling in the high latitudes in the Arctic. Because remember, this only operates in the northern hemisphere. It doesn't operate the same in the southern hemisphere, as we said in the last lecture. So we get ice buildup in the northern hemisphere. We get ice across the continents, across Siberia, across Northern America. We get a buildup of ice. And this ice is highly reflective, and so it can reflect the sunlight, the incident sunlight, back into space. It has a high albedo. And so this acts as a cooling feedback. You're getting less sunlight because we're going into a great winter here in the northern hemisphere, and the ice is reflecting any sun that does come in, and it's causing more cooling. So you get this cooling feedback, more ice, more cooling, and that generates an ice age ice sheet. And so we get this cooling, which, as you see in the red plot, goes on and on and on for 100,000 years. And during that 100,000 years, we do get more orbital cycle maxima. We get these Milankovitch maxima, what I call a great summer, where the amount of insolation, the amount of sunlight in the northern hemisphere increases. And you can see that in the two blue peaks halfway down. We get two quite large increases in solar sunlight hitting the northern hemisphere. And it does virtually nothing to the temperature. Why does it do nothing? Well, because the ice is bright white, high albedo, it's reflecting all of that incident sunlight away. So this cooling goes on and on and on, and effectively it could go on and on and on until the Earth entered something like a snowball Earth, where most of the Earth was covered in ice. So we've got to have some mechanism of stopping this increase in ice. And that comes about by CO2, because as we saw, as the world cools, temperatures fall, which increases oceanic solubility, which reduces CO2 in the atmosphere. And so CO2 goes down alongside temperature until it hits 180 parts per million at sea level. But high up on the Gobi Plateau, that's the equivalent of 150 parts per million. And that's enough to kill off all the plants and cause a CO2 desert, that term that they don't like to use. And it is this CO2 desert that causes the dust. As we saw, and as we can see here, you get a very large peak of dust. It's not just a small increase in dust, it's a huge increase in dust. And it's not just dust for a couple of years, this is dust for 10,000 years. And why for so long? Well, because the climate system is waiting. It's waiting for an increase in insolation again. It's waiting for another great summer. And so as soon as that increase in insolation comes along, as soon as we enter that great summer, the lower albedo ice, now because it's covered in dust, can melt. It can warm and melt. And it concentrates on the surface as it does so, increasing the concentration of dust and therefore increasing the warming feedback that the dust is given. And so we can have complete warming in 5,000 years, because these interglacial warming periods are very, very short. So we have an ice age for 100,000 years, say, and then the interglacial just takes 5,000 years to melt all of that ice, because we have this very, very strong feedback caused by ice albedo, by the dust getting on the ice sheets. So that is the ice age cycle. And in conclusion, what we see is something that has a great contrast to what we're normally told. It's actually low CO2 that causes global warming during the ice age cycle, by getting so low that the plants die off, causing dust. It's a very easy theory to understand, but it's never mentioned because it goes against the global warming industry or religion that they have created. There is lots of, let's put it the other way around. There is no money to be made in albedo, but there is lots of money to be made in CO2 as a warming feedback, because your taxes are increased, your energy bills are increased to try and mitigate this non-problem. And that money is flowing into the pockets of the green lobby. Climatology used to be an obscure branch of science located in a hut at the end of the university campus. But now quite often climatology, global warming, is a major spinner, money spinner, in universities and university grant systems. The last thing these institutions want you to know is that global warming during the ice ages is controlled by albedo, by dust on ice, and not by CO2. Well, I hope you've enjoyed this illumination lecture, and I hope you can join us again next time. Thank you.